Good day, I'm Norman Wildberger. We're on our way to establishing something of a new foundation for parts of linear algebra having to do with matrix theory. And the main two concepts are these ones that I introduced last time, that of a pixel and a maxil. A pixel is a very familiar object. It's just what we have in the past called a point. It's a two-list of natural numbers. So it's a list with two elements, both of which are natural numbers. And the type for that is pix. And then we defined a maxil to be a multi-set of pixels. Like this one here, M, consisting of the pixel 3, 5, 3, 5, and 2, 2. That's a multi-set, so it's a maxil. So we could introduce a new type, max, short for maxil. So we have pix and max, two new types of objects that we can work with. Now, because we like to visualize things geometrically and visually, we're going to here think about pixels as being visualized on a screen. And the screen for us will be this framework here, where we've arranged that the pixels are labeled like this: 1, 1, 1, 2, 1, 3, 1, 4, and 2, 1, 2, 2, 2, 3, 2, 4, and so on. And you can think about it alternately as a sheet which sort of extends to the right and down, divided into rectangular blocks, each block corresponding to one of these pixels. So this block here would be the block 2, 3, there. So the pixel 2, 3 can be visualized, if you like, as that little block in this screen. So this is an informal object. It's really not officially necessary. It allows us to visualize things, and it will allow us to connect more smoothly with this more familiar theory of matrices later on. But officially, what we're really just talking about are lists and multi-sets of lists. So it's really just a purely combinatorial situation at heart. So just a little bit of additional terminology. We'll say that the screen has rows. So these are the rows of the screen, and it has columns going this way. All right. At this level here, rows this way, columns this way. So in this video, we'd like to lay out a little bit more of the basic definitions and notations associated with these objects. So let's start with pixels. So we defined last time that a pixel is diagonal if it has the form NN. And the transpose of the pixel A equals MN is the pixel AT, standing for A transpose, which is NM. So we just reverse the order of the two entries. And we note that A is diagonal, that is of this form, precisely when it's equal to its transpose. And we might also observe that if we take the transpose of the transpose, then we get back to the original pixel. Good. And let's also say a little bit about the relationship between two pixels. So we'll say that A, which is say KL, and B, which is say MN, are row collinear precisely when K equals M, when the first two components are equal. Diagrammatically, that means they're in the same row of our screen. And correspondingly, they are column collinear precisely when the second entries match up when L equals N. That's telling us that they're in the same columns. And more generally, we'll say they're collinear precisely when they are either row collinear or column collinear. So they're either in the same row or in the same column. And sometimes it's useful for us to pick out what the row is or what the column is. So let's introduce this terminology, R, standing for row. So R of A, where A is a pixel, is the first entry M. It's telling us which row it's in. And C of A is the second entry, in this case N, which is the column that it's in. So we'll refer to this as the row of A, and this as the column of A. And these are the numbers, these are just the entries of the two list. All right, now let's turn to maxils. So a maxil is, I remind you, a multi-set of pixels. And this is its primary manifestation. So although we may end up visualizing a maxil in a number of different ways, in particular as a diagram in some two-dimensional screen, it's really primarily a multi-set of lists, of two lists. And that's its primary aspect of what it really is. So here is a Maxwell M consisting of 1, 1, 1, 1, 1, 3, 1, 4, 2, 2, 2, 2, and 2, 4. These are all pixels, and this is a multi-set containing those pixels. So a natural first thing to define is the size of a Maxwell. That's going to be obviously the size of it as a multi-set, the number of pixels that it contains. And of course, repetitions are included because this is a multi-set. And we'll use the same notation that we usually do for size. So for example, in this case here, the size is 7 because there are 1, 2, 3, 4, 5, 6, 7 entries or elements. Another kind of measure of how big a Maxwell is with this other idea, the idea of the extent of a Maxwell. So the extent of a Maxwell M is a pixel, E of M, which is R, C, where R and C are the largest rows and columns of pixels in M, respectively. So let me explain that. So what we're going to do to find R of this Maxwell is to look at the various R's of the various pixels in M, and we see that the biggest one is 2. All right. So the R value for this Maxwell will be 2. And what about the C value? Well, we look at the second entries, and we pick out the largest one of those, which is 4. So then the C is going to be 4, and the extent of M then simultaneously tells us sort of how far over we have to go in rows and how far over we have to go in columns to embrace all of the pixels which are in this multi-set. That's another way of sort of specifying, especially on the screen. It corresponds to sort of the smallest rectangle that we can create that frames entirely our multi-set, our Maxwell. We'll say that a Maxwell M is diagonal precisely when all of its pixels are diagonal. So it consists of pixels like 1, 1, or 4, 4, or 17, 17, and so on. The transpose of a Maxwell M is the Maxwell, denoted M to the T, of transposes of its pixels. So a Maxwell, like this one here, is a multi-set of pixels. If we take the transpose of each of these pixels, then we get the transpose of the Maxwell. So here we have 1, 1, 2, 3, 2, 3, 5, 1, and the transpose will consist of 1, 1, 3, 2, 3, 2, and 1, 5. Once we have the notion of the transpose of a Maxwell, then we can introduce this important idea of the symmetry of a Maxwell. We'll say that a Maxwell is symmetric precisely when it equals its transpose. That when you take the transpose, you get back the original Maxwell. Geometrically, it means it's sort of symmetric along the diagonal. If 3, 5 is a pixel inside it, then 5, 3 will also be a pixel inside it. And now let's have a look at the extent of a Maxwell and the relation with the extent of the transpose. So the extent of the Maxwell is sort of the size of the smallest box that it sits in. So if that happens to be RC, meaning that there are R rows and C columns, then the extent of the transpose is the transpose of the extent. In other words, the extent of M transpose will be the transpose of this extent. Now this is just a pixel, so its transpose is just CR. So if a Maxwell has extent 5, 3, then its transpose will have extent 3, 5. Makes sense. We've noted already that the smallest pixel is 1, 1, because we're not allowing 0 for the entries of pixels. The empty maxile is the smallest maxile. So a maxile is a multiset. A multiset is a collection of things. The simplest possible situation there is when that collection is empty. So the empty maxile looks like that. It contains no pixels. So its size is 0. We will give it a special name because it is a rather important object. So we'll denote it with this symbol capital O. So there's capital O, and it's the empty maxile. We'll call it usually the empty maxile, or maybe sometimes the 0 maxile. And here is the size of O is 0. What should be the extent of O? Okay, so that was a question of sort of finding the smallest rectangle that contains this thing. Well, I think if you think about this definition, it's a little bit ambiguous. So we're going to leave this as undefined. So this particular maxile does not have an extent. Other maxiles do, but for now this thing has an undefined extent. Let's talk about the realm of maxiles. Now start thinking about operations that we can perform with maxiles. So we've talked about the realm of natural numbers, and we've talked about the realm of multisets just a dozen videos or so ago. And what made the realm of multisets work is that when you have a multiset of objects, then each of the multiplicities is a natural number, or a natural number plus 0. Now, in this situation, we're talking also about multisets. They're no longer multisets of natural numbers, but they're multisets of pixels. But nevertheless, the multiplicities of any pixel can still be a natural number or 0. So exactly the same kind of reasoning that we used in discussing multisets of natural numbers applies now to this situation of multisets of pixels. In other words, maxiles. So the maxiles themselves are going to form a realm, just like the multisets of natural numbers did. So in particular, we're going to have operations, rather familiar operations of addition, union, and intersection. So for example, if we consider these three maxiles, there's M, 1, 1, 1, 2, 1, 2, 2, 4. Here's N, which is 1, 2, 1, 3, 3, 4, and O, which is 1, 1, 1, 1, 2, 4, 3, 4. Then M plus N, these are multisets, so plus just means addition of multisets. We just dump everything into one big box. So if we add M and N, we just get 1, 1, 1, 2, 1, 2, 2, 4, 1, 2, 1, 3, 3, 4. Everything just gets put together. If we say take a union, that means we're looking at multiplicities of objects and taking the union of the multiplicities, in other words, the maximum. And so the union M, union O, well, how many 1, 1s we have? Here there's 1, and here there's 2. So the maximum of that is 2. So this union will have 1, 1, 1, 1. And 1, 2, there's one of them there. And, oh, actually there's 2 of them in the M maxile, so there'll be 2 in the union. And then we have a 2, 4 here and a 2, 4 here. So the maximum of that is 1, so there'll be a single 2, 4 in the union. And then in addition we have a single 3, 4 there. So there's the union of M and O. In terms of intersection, well, it's just the minimum of multiplicities that we're looking at. So for example, if we take N and O, then the intersections, well, 1, 1s, there aren't any 1, 1s in here, so there won't be any in the intersection. There aren't any 1, 2s here, 1, 3s, no, 2, 4s, no. The only things that they have in common are the 3, 4s, so the minimum of the multiplicities of the 3, 4s is 1. So the intersection is the maxile consisting of the single pixel 3, 4. And something else that we can do in terms of operations with our multisets, multiplying them by a scalar. So if we take n and say multiplied by 2 to get 2n, just means we're repeating each of the pixels that are in there twice. So there's a 1, 2 here, so there'll be 2, 1, 2s. There's a 1, 3 here, there'll be 2, 1, 3s. There's a 3, 4, and there'll be 2, 3, 4s. And this is generally the convention that we'll use for these multisets, that if they need to sort of wrap around, we'll just wrap around like this, and you're supposed to remember that there's a left bracket there and a right bracket there to enclose the Maxell altogether. Okay, so this is pleasant. So now we can sort of go and back and look at all those various properties that we had for realms, and we can convince ourselves that the same kinds of things are going to be happening here for this realm of Maxells. For applications to linear algebra, the fact that we can add Maxells is really important. Okay, and the fact that we can take scalar multiples of them is really important. And when we combine those two things, it means we can take linear combinations of Maxells as well. So for example, if A and B are Maxells, then A plus B is a Maxell, so is 2A, so is 3B, and so is a linear combination like 2A plus 3B. And we're getting these operations for free. This is a very pleasant situation, that we don't have to define especially how to add and scalar multiply and then take linear combinations. These are automatic because we're working in this realm of multisets. Whenever we have multisets of a certain type, we can add them, we can scalar multiply them, we can take linear combinations. It comes for free. So if you've taken a linear algebra course, what we have here is the vector space or linear space structure of these Maxells, essentially coming to us without any work. And that's quite a pleasant aspect of things. But in addition, we have unions and intersections, things which don't get that much press in linear algebra usually. But we're also in a position of taking the union of two Maxells and taking the intersection of two Maxells. And I've already mentioned that the various realm laws that we discussed in these two videos, Math Foundations 155 and 156, hold also here, so you might want to refresh your memory on that and just check in your minds that things are going to be holding here. Alright, so that's all very nice, but what really makes things interesting is that we also have a multiplication. Now what's particularly pleasant about this multiplication is that it really starts at the pixel level. And the multiplication at the Maxell level is almost an automatic consequence of this fundamental multiplication of pixels. And I should probably warn you that this definition is a little bit unusual. It will be breaking new territory for you conceptually, probably, because of the unusual use of this blank space here. So let's have a look at it. So we have two pixels, KL and MN, and I'm going to tell you how to multiply them. So multiplication here is just when they're together, that means multiplication. And the rule is that if L equals M, if these two numbers agree, then the product is the pixel KN. Fair enough, that's very easy. But otherwise, the product is empty. You get nothing. And you really get nothing. You don't get 0 or the empty set or the empty this or that. You just get a blank. There's nothing there. So usually in mathematics, when we have a product structure in some context or another, we're multiplying two things of a certain type, we usually get a third thing which is of the same type. That's a typical kind of binary operation point of view towards multiplication. So that's sort of what we have here. I mean, we have two pixels, we're multiplying them together and we get a pixel. But only under this condition. Otherwise, we're not getting a pixel at all, because this empty blank is not a pixel. There is no empty pixel. So we're going outside the realm of binary operation here. This is something a little bit different. So for example, 1, 3 times 3, 7. In this case, these intermediate values are the equal, so the result is 1, 7. Here, 1, 3 times 2, 7. In this case, these intermediate things are not the same, and so the answer is nothing, this empty space. And in this case here, we have 2, 4 times 4, 4. So here the inside two elements are equal, and so we get the outside two, which is 2, 4. All right, so it takes some getting used to, but it's, I think, pretty clear-cut what you get. Okay, so here's a proposition that if A and B are pixels, then if we take AB and take the transpose, then we get B transpose times A transpose. So let's have a proof. So suppose that A is KL, like this, and B is MN, like this. Okay, and let's suppose, first of all, that L equals M. Well, in that case, when we multiply AB and take the transpose, the product AB is, just as it is here, Kn. So we're taking the transpose of Kn, and we know how to do that. We just interchange the entries here, and then we get Nk. And Nk is the same as Nm times Lk, because we're still under the assumption that L equals M. And this thing here is B transpose, because B was this, and this thing here is A transpose, because A was this. Now, suppose that L does not equal M. L does not equal M. Well, in that case, A times B is empty. And in that case, B transpose times A transpose. Well, B transpose will look like this thing, and A transpose will look like this thing, and if L is not equal to M, then we're in the same situation that that product is going to be empty. So the left-hand side is empty, and the right-hand side is empty, so, okay, it's still equal. So, okay, this is going to be a pleasant and important thing. But notice that it's at the level of pixels. Of course, this is familiar to you in the matrix form, but what we're doing here is we're just identifying this is actually at the level of pixels. This is happening. All right, so now here is a more serious theorem. So this theorem gets a name, associativity of pixel multiplication. And it is that if A, B, and C are all pixels, then AB times C equals A times BC. So we have associativity of pixel multiplication. Okay, I'm going to have to say a little bit about this. There's a kind of a special case here that our previous definition hasn't really covered, and I will discuss that during the proof. We'll start by introducing A to be KL, B to be MN, say, and C equals OP. Okay, so we're going to have to look at AB times C and A times BC. And let's look first at the case when L equals M and N equals O. So the inside ones here agree, and the inside ones of these two also agree. Okay, so if the inside ones here agree, then the product of AB is Kn. And then if N and O agree, then AB times C will be Kn times OP, which will be Kp. So this first thing will evaluate to Kp. On the other hand, this thing here, if we multiply B times C first, the N and the O we're agreeing are the same, that means we're going to get MP. And then when we multiply by A, we're going to get KL times MP, but we're agreeing that L equals M, so that'll give us Kp again. So under these two assumptions, both this and this evaluate to Kp. The first one of A and the second one of C. And the claim is that everything is empty otherwise. But we have to say, to be precise, what it means for an empty pixel to multiply by a regular pixel. We actually haven't defined the product of an empty thing with the pixel C. So we have to define that in that case, that product is going to be empty as well. Okay, that's the meaning that we'll assign if this happens to be an empty situation and we're multiplying by C, then the result is still empty. All right, so now we have to look at the cases when this is not happening. So if this is not happening, then AB is going to be empty, and this will be empty. What about this thing here? Well, this might be empty, in which case the whole thing will be empty, or it might not be empty. If it's not empty, it's got to be of the form M times P. That's the case when N equals O. But then if this is MP, then the fact that that M does not equal L, that's our assumption, will mean that this is going to be empty. Right? So if this is not true, then both of these are empty. And similarly, if this is not true, then both of these are going to be empty. So in either case, if we do not have both of these conditions, these two things are both empty. So our associativity is a theorem. You might like to ponder what happens if we have more than 3 pixels. Suppose we have A, which is KL, B, which is MN, C, which is OP, and another one, D, which is QR. You might like to show that then A, B, C, D is well defined. Again, that associativity implies that we don't need to worry about where the brackets go. And it equals KR. That's the first one here and the last one there. Precisely when L equals M, when these agree, and when N equals O, and when P equals Q. So if all of the interior ones sort of agree, then the product is not empty and we get KR. And otherwise, we just get an empty product. So it takes some thinking to work through this argument. Please give this some thought and convince yourself that this is sort of reasonable and that we really have this associativity at the level of pixels. Okay, very important. It's this associativity of pixel multiplication which really drives the entire structure in some sense. Having now a multiplication for pixels, we are going to jack this up to a multiplication for maxels, and that's really where this algebra is happening, at the level of maxels. And to go from this pixel multiplication to the maxel multiplication is really the invocation of a general principle, or it's a definition really that we're going to apply in other situations also later on. So if in general, in very general situation, if we can multiply objects A and B of some type to get, say, A times B, then in general we can multiply multisets of these objects. Okay, and we do that by considering all possible products with the correct multiplicities forming another multiset. So this is a very general statement that we're going to apply in a lot of different situations. We're going to agree that if we have some kinds of objects and we have a multiplication defined for them, and now we're considering multisets of those objects. So for example, here is some multiset of some objects, A, B, and C, and we don't really care what exactly those objects are. And here's another multiset D, same kind of objects as these ones, but we don't actually care precisely what they are. Then in order to multiply this multiset with this multiset, we're going to agree that what we're going to do is we're going to multiply each one of these ones with each one of these ones and put all of that, all possible products in a big box. Right? That's going to be our orientation to how we take products of multisets in a very general fashion. This is a very important idea. It's going to have major consequences for us in algebra. Like for example in group theory, we're going to see it's really going to be a very instructive idea. Okay, so to be precise here, we've got A, B, C in this multiset, we've got D here, and when we take the product, we're going to get the multiset consisting of A times D, whatever that is, A times E, B times D, B times E, C times D, and C times E. Right? We're just going to compute all those products and then put them all together in a big box. Right. So having said that, we don't really have to do anything separate for the maxel situation. We have a multiplication of pixels. Maxels are just multisets of pixels. So immediately the multiplication of pixels defines a multiplication of maxels. And let's give one final example of this kind of multiplication. So here's a maxel and here's another maxel. I'm going to multiply these two maxels. So this maxel contains the pixel 1, 1, 1, 2, 1, 2, 2, 3, and over here this maxel contains the pixels 2, 1, 2, 4, 3, 5. So in order to multiply these maxels, what we're going to do is we're going to multiply each one of these with each one of those. Okay, so let's do that. So 1, 1 times 2, 1. What is that? Well, to calculate the product, we have to check whether this entry here is the same as that entry there. That 1 and that 2 are not the same. So that means that the product is empty. In the big collective box, we're putting nothing. This product contributes nothing to the final multiset. Okay, so next one. 1, 1 times 2, 4. Again, the 1 and the 2 do not agree. We're getting nothing. This 1 times 3, 4. Again, we get nothing. How about 1, 2 times 2, 1? Well, now this 2 and this 2 do agree. And we're going to get, therefore, the outer ones, which is 1, 1. So there we get a 1, 1 there. So that's the result of this pixel times this pixel. Okay, what about this 1 times 2, 4? We're going to get 1, 4 as a result there. And 1, 2 times 3, 5, that gives us just emptiness. How about 1, 2? Well, that's the same story. 1, 2 times 2, 1, that's going to give us another 1, 1. 1, 2 times 2, 4 is going to give us another 1, 4. And 1, 2 times 3, 5 is going to give us another nothing, which doesn't contribute. And finally, 2, 3 times this is nothing, 2, 3 times this is nothing, and 2, 3 times 3, 5 is 2, 5. So we just have repeated pixel multiplication. We have to go through all these possibilities and take all possible products and put them all in a big box. Remembering that when we get nothing, well, we're putting in nothing. So there's no contribution. This is really fabulous. It's an elementary way of capturing matrix multiplication, a way that gives us a lot of things for free. For example, associativity, we'll observe next time, is pretty well automatic in this kind of situation. But this also gives us more flexibility. We're not constrained anymore to have a matrix of one size only multiplying a matrix of some other particular size. Any maxwell times any other maxwell, we can multiply them. We can do multiplication uniformly across the board with these maxwells. It's not a selective multiplication as you learn in traditional linear algebra. So reorientation will be partially necessary. I want you to forget a little bit, just a little bit, about what you know about regular matrix multiplication, at least just temporarily. Eventually then we'll come back and connect with that. All right, great. So we've introduced a lot of interesting, important things. Next video, we're going to go further in this direction. So more about Maxwell multiplication and its various ramifications and examples. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.